Hello everyone, and welcome to Chapter 1, our very first video lecture of this brand new semester of organic chemistry. And my name is Mike Cross, in case you were wondering. I know I'm just a voice behind the screen. But remember that I am here for you. I love organic chemistry. I think it's very exciting. I also admit that there are some parts of it that are extremely tedious. And so I'm going to do my best to help you to find the very useful parts. I'm going to do my best to minimize the unnecessary tedious stuff, but there is some parts that are tedious that are necessary, and that's just the way of life, right? Part of it really is just learning a new language of organic chemistry, and so that can require a lot of repetition and a lot of work, but it will be worth it in the long run. Now, one of the most important things to remember about this course, though, is that it does build on itself. So make sure that you're understanding things as we go along. Make sure that you're asking questions when necessary, because if there are gaps in your knowledge, then that's going to come back and bite you later on, because we will be using the same material over and over again. Okay, so speaking of possible gaps, we are going to be looking at Chapter 1, which is all about just looking back at general chemistry, which hopefully you've all been through, so that you can see what's really the essential stuff that you need to know from Gen Chem so that you can do well in OChem. All right, so let's take a look. First off, what is organic chemistry? The thing is that organic chemistry, they used to think that organic chemicals were special, that they came from living sources, whereas inorganic compounds just came from rocks. And so that was the big difference. It wasn't until later that they realized that you could take a mineral like ammonium cyanate, which everyone agreed was just a mineral, right? Just an unliving thing. And if you heat it up, you get urea, which is also found in animal urine. And so that is definitely an organic compound. So that's when they had to kind of change some of their thoughts on what does it mean for something to be organic. There's still some debate on this topic. We are going to use the general classification that organic compounds are compounds that contain carbon. Now, again, there can be exceptions. You might say, well, what about calcium carbonate, limestone? Is that really organic? Well, no, maybe not. But, honestly, does it really matter all that much that we have a specific definition? Basically, we're going to be looking at carbon chemistry. And, of course, carbon is a very special atom, special element. It's right in the middle of the periodic table from left to right. And so it does behave in a very specific way. So things that are on the left-hand side of carbon, things like lithium, sodium, potassium, gold, all of those are metals, and metals like to give up electrons. Non-metals, things that are on the right-hand side of the periodic table, things like nitrogen, oxygen, chlorine, sulfur, they tend to accept electrons. Carbon is right there in column 4, and so it likes to share electrons. So that's the first thing we need to remember, is that carbon loves to share. Second thing we need to understand is just some basics about how an atom really looks. And, we could get into quantum mechanics, and, we do have to get into a little bit, but we can have this kind of mental image of an atom being simply this big kind of cloud of electrons, right? So we've got all these electrons just kind of around the center, and then in the middle of that, we have our protons and our neutrons. Those are in the nucleus. Protons have a positive charge. Okay, neutrons have no charge, electrons are negatively charged. Pretty simple, right? If an element, an atom, is neutral, it will have the same number of protons and electrons. So carbon typically has 6 electrons because it also has 6 protons. That's it, right? If we gained electrons, we would have a negative charge. If we lose electrons, then we'll end up having a positive charge. Now, all carbon atoms happen to have the same number of protons. They have 6 protons, otherwise they would not be carbon, right? They would be a different element. But not all carbon atoms will have the same mass, and that's because they can have different numbers of neutrons. So those are known as isotopes, kind of different flavors of the same thing, of the same element. So carbon happens to have 3 common isotopes, carbon-12, carbon-13, and carbon-14. They all have exactly 6 protons. They have the same atomic number, but they have different mass numbers. And remember that the mass number is equal to the number of protons plus the number of neutrons. So it makes some math pretty easy. If I have a mass number of 12 and it has 6 protons, then it must also have 6 neutrons, right? So I could go ahead and just draw neutrons down there. So this one has 6. What about carbon 13? Well, it must have 7. What about carbon 14? Well, 14 minus 6 is 8, so it has 8 neutrons. Now, those electrons, despite that picture that I showed you of this nucleus in the center and these electrons just kind of in this big gushy electron cloud outside, they do have a very specific distribution. Now, these are areas of high probability of finding an electron. There's no way of knowing exactly where an electron is at any one point, but we can kind of get a feel for it, right? So, for instance, if it was, I don't know, 3 p.m. on a Tuesday afternoon, I can say, well, my son's probably home from school, so it's most likely that he's at home, and I can kind of narrow it down, right? Now, could he be somewhere besides that? Yeah, of course he could, right? But you get the idea. All right, so these electrons are distributed in shells. Kind of think of these as like layers on an onion. So the n equals 1 shell is the smallest layer, the smallest kind of center part of the onion, and then we've got bigger layers that go out from there, right? The shells kind of expand from there. N equals 2, n equals 3, 4, and 5, and so forth. Now, within each of those shells, we can have one or more subshell, right? And we call these, like S, P, D, and F. S is the lowest energy, then P, then D, and then F. We always fill things up from the lowest energy shell, so we start at n equals 1 and move out from there. We also start from the lowest energy subshell, which is S, and we fill it up from there. So, for instance, in the third subshell, I have an SP and a D subshell, right? So I know that I'm going to fill up the S first, and then the P, and then the D. That's, typically how it would work, right? Now, things do get a little crazy because some of those energy levels are very close together. So they don't fill up in a nice perfect order. You have to remember Aufbau diagrams from Gen Chem, but we're not going to get into too much of that, right? Because it turns out that carbon is in the n equals 2 energy level. So carbon only has an S subshell in its n equals 1 energy level, and an S and a P subshell in the n equals 2 energy level. Now, the S subshell can only hold 2 electrons. The P can hold, actually, let me back up for a second. The the S subshell contains 1 orbital. Each and every orbital, no matter what kind of orbital it is, maxes out at 2 electrons. So that means that if I have 1 S orbital, it maxes out at 2 electrons. Okay. If I have a P subshell, the P subshell actually contains 3 orbitals. Each one of those can hold 2, plus the 2 from the S subshell, giving us the magical number of 8. And that's where that octet rule that you've probably heard a million times comes into play. By having a completely filled S and P subshell, then that gives you 8 electrons, which happens to be very, very stable. So we can figure out how many subshells or how many orbitals are in each subshell just by counting by odd numbers. So the S contains 1 subshell, P contains 3, D contains 5, and F contains 7. Remember that each of those contains 2 electrons, or can hold up to 2 electrons. All right. So there are some terms that you may be familiar with from Gen Chem. The Aufbau principle just talks about how you fill things up, okay, which we don't really need to get into because we're only going to be worrying about the first 3 in most cases, right? The 1s, the 2s, and the 2p subshell, because that's what carbon has. All right, we could also talk about the Pauli exclusion principle that says that you can't fit more than 2 electrons into an orbital, but we already know that, right? Every orbital maxes out at 2 electrons. And then Hund's rule also applies that says that electrons don't pair up unless they have to. It's sometimes called the bus rule. Like you get on a bus with a bunch of strangers. If there's an empty seat, you're going to take the empty seat. You're not going to cozy up to some random stranger if you don't have to. All right, now I've already mentioned this, but just be aware that things that are in the first column of the periodic table like to lose electrons. Things like lithium and sodium and potassium, these alkali metals, they like to lose one electron in order to stabilize themselves. If you are on the right-hand side of the periodic table, then you're a nonmetal and you like to gain electrons. Things that are in column 7A, so the halogens, fluorine, chlorine, bromine, and iodine, they have 7 valence electrons. They obviously really want one more electron so that they can have an octet. So fluorine and chlorine and iodine, they will tend to gain 1 electron each so that they can form a fluoride ion or a chloride ion, giving themselves an octet. That makes them stable. Hydrogen's kind of an oddball because it can either gain an electron to form what's known as a hydride ion. That's an important term that you may not be familiar with, but hydrogen with a negative charge, we call that a hydride ion. Hydrogen also oftentimes will lose an electron, forming a hydrogen cation or a hydrogen ion, or we could even simply call it a proton, because hydrogen has 1 proton, 1 electron. If it lost that 1 electron, now it's just a proton. So throughout the semester, you're going to hear me talking about protonating something or deprotonating something. That simply means attaching a hydrogen ion to it or removing a hydrogen ion from it. All right. Now, when it comes to organic chemistry, we don't tend to gain or lose electrons very often. Instead, we really like to share electrons, and we're going to do that in order to stabilize ourselves, right? So if we looked at a fluorine atom, it has 7 valence electrons. I know that because it's in column 7A on the periodic table. So look at the top of the periodic table. Hopefully it's labeled 1 through 8A using Roman numerals. If not, you can label it yourself, right? Just look at the main group elements, those ones that are sticking out of the top of the periodic table, right? So periodic table typically looks, something like this, right? Okay, so the main group ones would be these ones here, and then these ones over here. Okay, those should be labeled 1 through 8A using Roman numerals. Oops, switch that over. 1A all the way through 8A, going, starting here, and then 8A would be the noble gases way over there. Okay, anyway, so now that we can see that fluorine is in column 7A, we know that it has 7 valence electrons. We're going to represent those as the dots that are around it. Then we know that another fluorine atom can come in. It also has 7 valence electrons. Now, they don't really want to either give up or lose electrons because both of them want 8, and so they can't exchange electrons and still give everyone 8. So instead, they're going to form a covalent bond. Covalent bond always means a shared pair of electrons. So that's important to remember. It's a pair of electrons. We typically will draw that as a line in between them. That line, remember, simply means 2 electrons that are being shared between those 2 fluorines. Okay, next we could have hydrogen, and actually let me back up for a second. Notice that in the process of doing this, each fluorine here has exactly 8 electrons around it, right? The fluorine on the left has 2, 4, 6, 8, as long as we are counting those little dots around it, right? And so that means that there are exactly 8 electrons around the fluorine on the left. There are exactly 8 around the fluorine on the right. Notice that we're double counting those electrons in the center. That's perfectly fine. They're being shared, so we can count them for both of them. Most elements want 8 electrons. Hydrogen is an oddball. Hydrogen can only handle 2 electrons. So notice that when we form a hydrogen molecule, hydrogen on the left and hydrogen on the right each only have 2 electrons because of that single bond between them. That's important to remember, that if you ever see a structure or you ever draw a structure where hydrogen is bonded to more than one thing, it's wrong, because hydrogen maxes out at 2 electrons. It can only handle 1 bond. Okay, now what if we mix a hydrogen and a chlorine? Well, we can do that, and in the process, notice that hydrogen gets 2 electrons surrounding it, whereas chlorine gets 2, 4, 6, 8 electrons surrounding it. Everyone's happy, right? And I'll say that throughout the semester that, the atoms are happy. I mean thermodynamically stable because they have, a full octet, or in hydrogen's case, a duet. So you get the idea. Now, what if something needs more than one bond in order to become thermodynamically stable, in order to be happy? So let's look at oxygen. Oxygen happens to have 6 valence electrons. We know because it's in column 6A on the periodic table. So when oxygen bonds with hydrogen, it's going to need to bond with this hydrogen as well as another hydrogen, because now if you count the electrons around it, we have this lone pair, that's 2, this lone pair, that's another 2, this bond, that's another 2, this bond. So that gives us a grand total of 8 electrons around it. Nitrogen would have to bond with 3 hydrogens. Carbon would have to bond with 4 hydrogens. Okay. Now, those bonds, we talk about them being a sharing of electrons, right? But it's not always an equal sharing of electrons. I've got 3 kids. My 2 oldest are girls, and when they were young, I would oftentimes bring home a new toy or a periodic table or something cool for them to have, and they would always be so excited about it, but I'd often only bring home one, and I'd tell them that they would have to share it, right? Now, so they would be sharing it, and everything would look fine until I'd leave the room, and then suddenly I'd hear crying, and I'd go back in because when they were sharing, it's not always an equal sharing. Typically, the older one would share, quote unquote, share it more often because she's bigger and meaner and fights dirty, and so she'd pull the toy towards her, and my other daughter would be left out in the cold. So the same thing happens oftentimes when we are bonding atoms together. Okay? If I try to bond a hydrogen and a chlorine together, they share that pair of electrons that's in between them, but it's an unequal sharing. What that means is that chlorine has a higher electronegativity, so it ends up pulling on the electrons, and so the electrons spend most of their time surrounding the chlorine, and poor little hydrogen only gets a little bit of electron density. And so we represent that by using delta plus and delta minus. That's a Greek letter delta, lowercase Greek letter delta, and so it looks like that, right? Delta plus simply means that it has a slight or a partial positive. Delta minus means it has a slight or a partial negative charge. So you can see in this case the hydrogen gets a slight positive, the chlorine gets a slight negative. Same thing happens anytime we have what's known as a polar bond, something where it's an unequal sharing. Oxygen has a higher electronegativity than hydrogen, so it gets the slight negative, whereas the hydrogens get the slight positive. How do you know what the electronegativity is? Well, you could look it up on an electronegativity chart. That works. The easiest thing to remember is that electronegativity increases as you move up and to the right on the periodic table. So if I have my lovely periodic table over here, oh, sorry about that. There we go. I know that things that are in the top right will have the highest electronegativity, ignoring the noble gases, okay, because they don't want extra electrons, right? But something like fluorine has an extremely high electronegativity because that's just what it has. It's in the top right-hand corner. Something like cesium that's in the bottom left-hand corner would have an extremely low electronegativity. So when in doubt, simply look at where an element is on the periodic table. If it's something like a fluorine, a chlorine, an oxygen, a nitrogen, those are all in the top right-hand corner. They're going to have extremely high electronegativity. Something like carbon or hydrogen, not so much. Now, let me back up one second. Notice that sometimes we do have a nonpolar bond. So polar means that it's an unequal sharing. Nonpolar means it is a completely equal sharing. This really only occurs if we have 2 twins, right? If I had twin girls, they would have the exact same strength, so when they share, it really would be an equal sharing. So 2 fluorines, 2 chlorines, 2 carbons, 2 hydrogens, those would all be nonpolar bonds. Also, if you have a carbon and a hydrogen bonded together, we consider that to be a nonpolar bond as well. Carbon does have a slightly higher electronegativity than hydrogen, but the difference is very, very slight. Carbon's 2.5, hydrogen is 2.1, so it's a difference of 0.4, a very tiny difference. So that is important to remember because most of the molecules that we have are going to consist of carbon-carbon and carbon-hydrogen bonds. Okay. If you see a heteroatom, something like a fluorine thrown in there or an oxygen, now you've got a polar bond. Now that difference in electronegativity can be greater or less, right? And it really just kind of falls on a continuum. Now, there is a chart that you could use to figure out if something truly is a polar bond versus a nonpolar bond versus an ionic bond. You simply just subtract the different, just get the difference in electronegativity. So subtract the smaller number from the larger number, and you'll get a value, right? So, for instance, if I had, let's see, you'd have to get a chart for these, but let's say I have a fluorine bonded to a carbon. So fluorine happens to be 4.0, carbon is a 2.5, so the difference there would be a 1.5. That would fall right about here, and so notice that that is a polar covalent bond. Okay. If I had an ionic bond, something like, let's say I had fluorine and sodium. Sodium is much, much lower. I think it's about a 0.9, if I remember right. So 4.0 minus 0.9 for fluorine bonded to a sodium atom. That gives me a difference of 3.1. Oh yeah, that's way over here, right? So that would be considered an ionic bond. That's a complete transfer of electrons. I do not expect you to memorize the periodic table. I do not expect you to memorize an electronegativity chart, but I expect you to at least be familiar with the trends, right? So remember, high electronegativity is in the top right-hand corner. Now, in the process, we could measure what's known as the dipole moment. This is just measuring how big of an electronegativity difference there is. Now, the next big thing would be Lewis structures. This is vitally, vitally important for organic chemistry. So I really hope that you have a strong understanding of how to draw Lewis structures, okay, and what they mean. If you don't, then I'll put a link to a video I made for one of my earlier chemistry classes down in the description about drawing molecules. So you can click on that, go back and review it if you need it. Otherwise, as long as you remember how to draw a Lewis structure, you should be okay. Now, when we draw Lewis structures, sometimes you can draw more than one valid Lewis structure, and so we may need to be able to decide which version is better, which drawing is better, and one of the ways to do that is by calculating formal charge, okay, which is simply you just take the number of valence electrons something has. So I'll just give you a quick example. Let's say that I have a carbon that's bonded to 4 hydrogens, like that. And I want to know what's the formal charge on that carbon right there in the middle. Okay, so pretty simple. All I would do is I'd figure out the number of valence electrons that carbon has, which is 4 because it's in column 4A. And then I just need to subtract the number of lone pairs. I don't see any lone pairs on this carbon here, so that would be 0. And the number of bonds, 1, 2, 3, 4 bonds. So that comes out to be 0. So carbon would have a formal charge of 0 in that case, which is great. A nice stable molecule will often have formal charges of 0. Or a better way to say that is if you are looking at a series of structures, the most stable one will typically be the one with the formal charges closest to 0. Now, when we are doing formal charges, we don't oftentimes have to calculate these in organic chemistry, but you will see sometimes when there is a positive or a negative charge on an atom. And that is simply because we calculated formal charge at some point and put the charge there. Now, one of the important things to remember about that, though, is that there are some common bonding patterns that you can become familiar with. It does not mean that these are always the case. For instance, here it says that carbon forms 4 bonds. You will find times when it doesn't form 4, when it might have 3 bonds. That's fine, right? But these are the common bonding patterns. These are the most stable kind of conformation for it, where you won't have any formal charge on it. So these are important to remember. So first off, carbon likes to form 4 bonds. Now that could be 4 single bonds, it could be 2 double bonds, it could be a triple and a single. Anything like that works as long as it adds up to exactly 4 bonds. If I have 3 bonds and no lone pairs, I make what's known as a carbocation. That is a really important term to know. We're going to be using that all the time. So a carbocation is simply a carbon with a positive charge. a carbon cation. Okay, a carbanion is another important term. We won't see that quite as often, but it's still important. This is a carbon that has 3 bonds. It also has a lone pair, which gives it a negative charge, carbanion. Next, we may also have a radical. A radical is something that with an unpaired electron. So notice that it has just a single electron there, so we call that a radical. Now, if all of those look weird to you, good. They should look weird. They should not look terribly stable because they're not, right? Carbon likes to have 4 bonds. If it has more or less than that, well, carbon can't make 5, but if it has less than that, or if it has just lone pairs, if it has unpaired electrons, anything like that, it's going to make it unstable. Doesn't mean it might not form, but it means it will typically try to form something else as soon as possible. So if carbon likes to make 4 bonds, nitrogen likes to make 3 bonds, and oxygen likes to make 2 bonds. So pretty simple. In fact, if you look at the periodic table, you'll notice that these are kind of listed for you, right? Because you've got carbon, next door to carbon you've got nitrogen, next door to nitrogen you've got oxygen, next door to that you've got fluorine and the halogens moving down. So you can probably note some trends here. Carbon likes to make 4 bonds, nitrogen likes to make 3, oxygen likes to make 2. What do you think the halogens are going to make? 1, right? So hydrogen and the halogens like to make just 1 bond. Okay, pretty simple. All right, so here's just some examples of what these common bonding patterns mean and what you will typically see in a normal molecule. Okay, so we've got our Lewis structures here kind of drawn out. You'll notice that they will show the bonds themselves, which are shared pairs of electrons. They also show what are known as lone pairs, these unshared electrons. We could have double bonds, we could have triple bonds, right? On each of these you can see we may have a double, we may have a triple bond, and that's great, right? So those are Lewis structures. Again, watch the video in the description if you need extra help on drawing those. Now another tool that we use in organic chemistry are known as Kekulé structures. Because it turns out organic chemists are lazy. When we're drawing these things, it takes a lot of work to draw complex molecules. So we'll often look for shortcuts, ways to make it easier on ourselves. So notice that Kekulé structures look very similar, if I back up, to the Lewis structures. So what do you see as different about them? On the Kekulé structures, we're lazy and we're leaving off lone pairs, right? We should know, for instance, that this oxygen here should have, it's hard to draw with that stylus, but should have 2 lone pairs, right? A total of 4 unshared electrons around it. Okay, but if we're drawing Kekulé structures, we can leave those off. That's great as long as you are familiar enough with these to realize that they do have lone pairs, and they have enough lone pairs to give each atom an octet. We can also get even lazier and draw a condensed structure, right? So in this case, okay, so CH3Br, what that means is that I have a carbon bonded to 3 hydrogens. That's where the CH3 comes in. That's then bonded to a Br. Okay? It's important to note that you have to kind of piece together this in your mind. Sometimes people think, well, it's labeled as CH3Br, and so that means I have a carbon that's bonded to the hydrogens in the middle. So there's a ring of like 3 hydrogens like this, and then that's bonded to a bromine. No, that does not work, right? Remember that hydrogen can only make 1. I got to erase that. That just scares me. I can't even look at that. Okay, so just be aware that carbons are like the nice central atoms, and you just have to kind of piece it as you go through. So as I'm reading this one here, for instance, I read this as a carbon bonded to 3 hydrogens, bonded to, and that carbon's also bonded to an oxygen, which is bonded to another carbon, which is then bonded to 3 hydrogens. Sure enough, that's how the drawing looks, right? Here's my CH3, okay? My carbon bonded to 3 hydrogens, then bonded to an oxygen. That oxygen's then bonded to another carbon. That carbon also happens to have 3 hydrogens on it. Okay, so we can also kind of do a mix between the two. We could do a condensed structure that also happens to show where things branch off. So see how this, I have my condensed structure, but I also show that those CH3 groups are branching off from one of those central carbons. All right, you can also try to summarize things if you really want to by putting parentheses and then like a 2. So this shows that I have, here's my carbon chain. It has 2 of these CH3 groups branching off. Okay. But I don't typically stick with those. Oftentimes I will draw skeletal structures because A, they are pretty much the easiest thing to draw out of all of these, and B, because they're called skeletal structures, and I grew up watching He-Man, and so I always think of Skeletor, and it makes me chuckle. So anyway, I will always call them skeletal structures. Some people call them line bond drawings, which I think just sounds silly, so I will personally call them skeletal structures, which is what many books will call them. Okay, so how do these work? Well, as I mentioned, this is a shortcut notation. So what they are showing is wherever you have the ending of a line, like right here, that represents a carbon. Also, where 2 lines meet, kind of like a vertex, a corner, that is another carbon. So here I have 1 carbon, 2 carbons, 3 carbons, 4 carbons, which are then bonded to a bromine. If I look at my actual condensed structure, sure enough, I've got 1, 2, 3, 4 carbons, which are all in a straight line, bonded to a bromine. Okay, same thing here. I have 2 carbons. Sure enough, I've got 1 carbon, 2 carbons, then an oxygen, then I've got another carbon. Okay, I could even draw ring structures, right? So here I have a total of 1, 2, 3, 4, 5 carbons that are all bonded in a ring. So sure enough, I've got 1, 2, 3, 4, 5 carbons all bonded in a ring. I can even represent double bonds in the same way, right? Like in this benzene molecule here, I have 1, 2, 3, 4, 5, 6 carbons in a ring. Okay, sure enough, they're all in a ring. And sure enough, I can also draw wherever there's a double bond, I can draw that double bond here, right? So hopefully you kind of get the idea. Let's go ahead and try doing one of our own. So let's say that I gave you this structure here. So let's say that I drew that structure and I asked you to kind of piece it together. Well, first off, I need to figure out how many carbons I have. So I've got 1, 2, 3, 4 that are in this ring. Okay, so let's go ahead and draw those. Okay, so I've got a carbon, 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 carbon. So 4 in a ring. Next, notice that I have a chain coming off of that top right-hand carbon, and I've got 1, 2 carbons in that chain, and then followed by an OH. So here I've got a carbon, then another carbon, then an OH. All right? Now, the other thing that's missing from both of these structures would be the hydrogens. With skeletal structures, you are not supposed to draw in the hydrogens that are attached to carbons. We call those implied hydrogens. Basically, they would just gum everything up. They would make everything look very cluttered. They would not spark joy, as Marie Kondo would say. So, therefore, I get rid of them, right? I don't draw them. I just know that they are there. So, if I wanted to draw in my implied hydrogens, I could do that. I could see that this carbon right here has 2 bonds coming off of it. So it needs 2 hydrogens. Same thing with this one. It needs 2 hydrogens. Same thing with this one. It needs, oh, it's coming off the page there, 2 hydrogens. What about this carbon in the top right-hand corner? Notice it already has 1, 2, 3 bonds, so it only needs 1 hydrogen, because how many bonds do carbons like to make? 4, right? Now, what about this carbon that's part of the chain? It already has 2 bonds, so therefore it needs 2 hydrogens. Same thing here. Now, notice the hydrogen is already attached to that oxygen, because with skeletal structures, you only leave out the implied hydrogens, the ones that are attached to carbons. You always draw in the ones that are attached to heteroatoms. So if you have a hydrogen attached to a sulfur or an oxygen, you have to draw those in. So if I really wanted to, I could also specify the lone pairs that are found on this oxygen. I know that there are 2 lone pairs there because that would give me a total of 8 electrons around that central atom, that central oxygen. Okay, so those are skeletal structures, right? They're not too bad. They take a little bit of practice, but as long as you see that, they really do kind of make your life simpler. Oftentimes I will draw molecules as, just skeletal structures simply because it's easier, right? It's easy for you to see it and easy for you to focus on where kind of the critical chemistry is happening without all those extra hydrogens cluttering things up. Okay, so to change pace just a little bit, that is one of those weird tools that you will see a lot. There are a couple of weird tools and techniques that we use in organic chemistry. The first is drawing skeletal structures. That's probably something new. Another one is arrow pushing, which we're going to talk about in a later chapter, but you're going to see that forever till you have nightmares about it. But just to take a little mind break for a minute, let's go ahead and take a look at another weird tool that you might see. Okay, I've got a little plunger here, right? Tiny plungers are useful for all kinds of stuff. I carry it with me everywhere I go. It's also great for magic tricks. So if you name a number, let's say 7, I can go ahead and push down on the plunger, and it will give me exactly 1, 2, 3, 4, 5, 6, 7 cards, right? That's great. Plungers now know how to count to 7. I could also have you choose a card, okay? Let's say you choose this one, okay? Now I'm just going to go ahead and put that back on top, and then normally I'd have a student do this. You would cut the deck for me, and I'll just mix that in there. But luckily the plunger knows your card, and I can pop straight to it, right? So again, plungers are great tools for doing weird things like magic tricks. Skeletal structures, arrow pushing, things like that are some weird tricks, weird tools that you're going to learn to use in organic chemistry. It's okay if it seems a little odd now. Hopefully it will start to make sense as we use it throughout the semester. Okay, so let's go ahead and let's backtrack a little bit to looking at where those electrons are actually located in an atom. Now, I mentioned that there are s orbitals. S orbitals happen to be spherical in nature, okay? So the 1s is like a tiny sphere, the 2s is a larger sphere, the 3s would be an even larger sphere. The p orbitals are dumbbell-shaped. I always learn them as peanut shape, p for peanut, s for sphere. It helps me to remember it. But remember that these p orbitals, there are 3 of them, and they go along in the x, the y, and the z directions, okay? So that's important that we know that there are 3 of them. It's also important that we remember their orientation in space. You're going to see why a little later. Now, if we have 2 orbitals that directly overlap, we form what's called a sigma bond. So sigma, sometimes just abbreviated with the lowercase Greek letter sigma, like that. So a sigma bond is a very strong bond. It's a direct overlap of 2 orbitals. Okay? So in this case, if I have 2 hydrogen atoms, this one has its own little s orbital, and this one has its own little 1s orbital. When they come close together, you notice that we get some overlap between that. So that's a sigma bond. We now can form a molecular orbital. Basically, they pool their electrons in a little bit of atomic socialism here, and now we just consider that they put their electrons into this molecular orbital. Now, if you remember learning a little bit about quantum mechanics in Gen Chem, you saw that we can actually treat electrons not as little point charges, but instead as probability waves. And we know that waves have a tendency to either reinforce each other or cancel each other out, right? If I drop, 2 pebbles into a nice still pond, I can actually watch as their waves come together, and some of them cancel out, and then you get perfectly smooth areas of the lake. You also get some where the waves get larger because they've constructively interfered with each other. Other times they destructively interfere and cancel each other out. So the same thing can actually happen with our electrons as their probability waves overlap. Whenever they constructively interfere, we get what's known as a bonding orbital. Okay? So when they constructively overlap, we get, in this case, a sigma bonding molecular orbital. But every time you make a bonding orbital, you also make an anti-bonding orbital. Okay, and as the name implies, bonding, if we put electrons in there, then the molecule bonds together. Okay, the atoms bond to each other. If instead we put electrons into an antibonding orbital, then they cancel out that bonding orbital and the molecule falls apart. Okay, this actually helps to explain, if you remember from Gen Chem, why something like H2 works great, right? Because each one brings one electron to the party, right? So we've got one up here and one down here. And so when they overlap, they go into the bonding, the sigma bonding orbital, and we get a bond, right? Now, if we had something like dihelium, 2 helium atoms, each one brings 2 electrons to the party, right? So I would have 2 in each one. So the first 2 would go down here, just like before, right? One up, one down. But then I still have 2 more. Those would be forced into this antibonding orbital up here. Because they're in that sigma star antibonding orbital, they would then negate, let me get a different color here, okay? These 2 in this antibonding orbital would negate the bond that was formed in this antibonding, and my dihelium molecule would simply fall apart, which explains why helium does not bond, right? It does not make molecules. Now, if that works with sigma bonds, right, with the direct overlap of those orbitals making a sigma and a sigma antibonding orbital, we can also do the same thing with p orbitals making what are known as pi bonds. Okay, so in a pi bond, first off, we need to remember that it is a sideways overlap. Okay, because if I back up for a second, remember how when these overlapped, these s orbitals overlapped, we were getting a direct kind of head-on overlap between the two. With a pi bond, we are getting these p orbitals, okay? And with p orbitals, they end up overlapping this way, okay? Kind of a sideways overlap. It's not nearly as strong as a direct overlap. So pi bonds are not nearly as strong as sigma bonds, okay? Simple as that. But you get the same thing. You can get pi bonding and pi antibonding. Now, why does all of that matter? Why do we care so much about this? Well, because we need to explain the shape of our molecules. So let's look at the simplest organic molecule, methane, a carbon with 4 hydrogens around it. From studying this, scientists have found that this carbon is surrounded by the 4 hydrogens. They all have the exact same bond length, which comes out to be about 1.1 angstroms. They also all have the same bond angle, which comes out to be 109.5. So that's what a methane molecule looks like. Pretty simple, right? But trying to explain that actually doesn't make a lot of sense, because if I have a carbon and 4 hydrogens, that carbon needs to be able to make 4 bonds. And you only make a bond when you have a half-filled orbital, right? So what that means is that this carbon, because its electron configuration is 2s2, 2p2, right? So it has these 4 valence electrons. So what it means is that it must actually be promoting one of its s electrons into a p orbital. That would make sense, because now notice that I have 1, 2, 3, 4 half-filled orbitals. So therefore the 4 hydrogens should be able to come in, and they should be able to bond with each of those, right? And that's how I would make CH4, is by bonding with each of those. Okay, that sounds great, but what do you notice about this? Well, the S and the P's are different, right? The P's are higher in energy. They also have a completely different shape than an S, right? Remember, the S is spherical, and the P's are dumbbell shaped, right? And so how in the world would I be able to get this beautiful little structure over here with 4 identical bonds if they don't make identical bonds? So instead, I need to invoke something known as hybridization. So hybridization basically means that we are going to take those 4 bonds, or those 4 orbitals that I mentioned, an s and 3 p orbitals. We're going to blend them all together, and we're going to spit out 4 orbitals that are identical, what we call hybridized orbitals. They are specifically called sp3 hybridized orbitals because they consist of an s orbital and 3 p orbitals that have all been put together and then blended up to make 4 identical sp3 hybridized orbitals. Okay, I kind of think of it this way. Let's say that you and your buddies, there are 4 of you all together, and that you really want to, well, actually, back up. Let's say that there's you, and you are trying to make smoothies for your 4 buddies. Okay, and just like carbon is trying to make bonds with these 4 hydrogens. So that means that carbon needs to send its electrons in 4 different directions, right? So that it can send its electrons going to each of these hydrogens, but we want them to be equal. You don't want one of your friends to get a different smoothie than everyone else. And so what you do is you would look in your fridge and you'd say, okay, I have a strawberry, and then I also have 3 pieces of pineapple. So I could either make 1 strawberry smoothie and 3 pineapple smoothies, but then the 4 hydrogens would be getting different things, and I don't want that, right? So instead, why don't I go ahead and blend them all together? I'm just going to put the strawberry along with the 3 pineapples in, and at the end of the day, I'm going to get out 4 smoothies, right? Those 4 smoothies will all be identical. They will all be sp3 hybridized smoothies, right? Because each one contains part of that strawberry and part of the 3 pineapples, right? And they'll be identical. That way, as I send those out to my 4 little hydrogen buddies over here, everyone gets the exact same thing. And so that's really all you're doing with hybridization. You're trying to mix and match these so that they're all identical. You can do this with pictures as well. So here we have our s orbital, which is spherical. We have our 3 p orbitals, which are dumbbell shaped. When we hybridize those, we end up getting 4 identical orbitals, these sp3 hybridized orbitals, and they look kind of like a mix between a spherical s and those 3 dumbbell shaped p's. The nice part about this is because they're identical, we can actually put those around the carbon, and if you can see from these drawings down here at the bottom, that means that we can now put them, point them towards the corners of a tetrahedron, bond angles of 109.5, and it exactly explains why our methane molecule looks the way it does. We could do the same thing with ethane, right? Now, how do I know that there is sp3 hybridization in my ethane molecule? Well, all I need to do is I need to look at this carbon right here, and I need to figure out how many different directions it needs to send its electrons. It needs to send some going up, left, down, and right. 4 different directions, right? So, therefore, I need to put in 4 different orbitals, right? So I'm going to go ahead and I'm going to put in an S, a P, another P, and another P. That gives me 4 orbitals, right? And so when I blend those together, I call those sp3 hybridized orbitals. Same thing if I were looking at this carbon over here, right? It also sends its electrons in 4 directions, so that carbon is also sp3 hybridized. What about the hydrogens? So hydrogens can't hybridize, right? Because they don't even have any p orbitals. Also, because they only need to send their electrons going one direction, right? I apologize for the music reference there, if you can call it music, but anyway, 1D. So if you only have to send your electrons going one direction, then all you need is an S. So on an exam, if I asked you what's the hybridization on this hydrogen, or on any hydrogen, you would just say unhybridized S, right? If I said what's the hybridization on this carbon, you'd say sp3, because it has to send its electrons 4 directions, therefore sp3 hybridized. Okay, we're going to kind of skip through this. It just shows that the same thing applies when we're mixing sp3 hybridized orbitals versus regular s orbitals. But let's get to some more interesting stuff. What if I gave you this molecule, ethene, common name is ethylene, and if I said, what is the hybridization on this carbon right here? Well, just like before, you'd say it needs to send its electrons going up, down, and to the right. So remember that hydrogen comes with 4 orbitals. So if I only need to send my electrons going 3 directions, I'm going to put in an S, a P, and another P, right? So I'm going to make sp2 hybridized orbitals, okay? And then I can send those going 1, 2, 3 different directions. Now notice that by doing this, I also happen to have this p orbital left over right here. So that p orbital is unhybridized, so it's still just a normal p orbital. That's really, really important for this because when I draw my molecule, okay, I have my normal p orbital that's kind of going up and down in this case, and then I have my sp2 hybridized orbitals. So look at what that looks like when we actually draw the molecule. So notice that we've got our molecule here, right, that's completely flat. But that unhybridized p orbital here going up and down, as well as the unhybridized p orbital on this carbon going up and down, and can you see how they can sideways overlap? So they just made a pi bond, right? That's the pi bond is the sideways overlap of those unhybridized p orbitals. That explains why in that molecule I have a double bond, right? So here's my molecule right there, and if I were to try to highlight each of these, I would say this is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. This first one is a sigma bond, but then the other one is a pi bond, right? Okay, excellent. And that pi bond is caused by that sideways overlap. All right, what about ethyne, commonly known as acetylene? Well, if I asked you what's the hybridization on this carbon right here, you would say, well, this one only needs to send its electrons going to the left and to the right. It only needs to send its electrons going 2 directions. So out of my 4 orbitals, really I only need to use an S and a P. So what would the hybridization be? sp hybridized. Okay. Notice that that still leaves me with 2 unhybridized p orbitals. Okay. So therefore, what do those p orbitals do? They allow you to make the double and triple portion of that bond right there. So the single portion is made by the sp hybridized orbital overlap, and then the second and the third part of that bond are made by the unhybridized p orbitals between those 2 carbons. Okay, we could draw this. It's a little harder to kind of visualize it, but what we're seeing is that the molecule itself is linear. It's the straight line, right? The carbons, the hydrogens all line up, but then we happen to have this up and down overlap between the 2 carbons and their p orbitals, but we also happen to have this left and right overlap between those unhybridized p orbitals. Okay, that explains why we have this molecule, right, being all straight down the line, and then we have our 2 pi bonds that compose that double bond and that triple bond, right? The 2 pi bonds within that. Okay, now what about some weird cases, right? I mean, it looks like you're probably going to be able to figure out what's the hybridization on a molecule, but what about if I'm missing some electrons? Okay, well, let's look at a methyl cation, right? So in that carbocation, notice that my carbon only needs to send its electrons going 1, 2, 3 different directions. So 3 different directions is sp2, right? Because that gives me 3. There is an unhybridized p orbital. There's nothing in it because there's no lone pair there. Okay, what if instead I had a radical? So notice I still have to send its electrons going in 3 directions. So that is still considered sp2 hybridized. Now the weird part about this is you might say, what about that radical, that unpaired electron? It turns out that that unpaired electron exists in this unhybridized p orbital. So that's the one that always gets me, is trying to remember that a methyl radical is actually sp2 hybridized. It's still a flat molecule with the unpaired electron in that p orbital. Now if I had a carbanion, this methyl anion right here, then what's going on? Well, it has to send its electrons going 1, 2, 3, 4 different directions. 4 different directions is sp3. Okay, so just remember that, right? If you need to count how many different directions your electrons are going, so look for bonds. Okay, count how many different directions you need to go with bonding electrons, as well as lone pairs. Okay, do not count unpaired electrons, right? Like in my radical from earlier, I do not look at this and say, oh, this one has to send its electrons going 1, 2, 3, 4. I don't count that last one, right? I'd say there's only 3 directions, so that would be sp2 hybridized. Okay, hope that's making sense. All right, so same thing happens with anything with a lone pair. If I gave you this ammonia molecule and said what kind of hybridization, you would say, well, nitrogen needs to send its electrons to the left, up to that lone pair, right to that hydrogen, down to that hydrogen. That must be sp3 hybridized, and you'd be right. Okay. You can go through and look at all these, fancy diagrams and stuff if you really want to. Same thing if this was an ammonium ion. There's no lone pair here, but I just count, oh, I have to send my electrons going 4 different directions. 4 different directions is sp3 hybridized. What about water? Well, same thing as before. I'd say, well, this center oxygen has to send its electrons going up to that hydrogen, to the right to that lone pair, down to that lone pair, and to the left to that hydrogen. So guess what? sp3 hybridized. Okay, sure enough, that's what you get. Bond angle in water is about 104.5. It's not the perfect 109.5 from a tetrahedron, simply because these electrons here that are in their, these lone pairs, they take up extra space, so they end up squeezing those 2 hydrogens together a little more than they normally would. Okay, now switching gears a little bit again, let's go ahead and look at what's happening with a hydrogen halide, right? So halogens, halides, are in column 7A, fluorine, chlorine, bromine, iodine, and so forth. Well, we know that they like to form one bond, right? Hydrogen likes to form one bond, halogens like to form one bond, so it makes sense that they would bond together. So that's pretty easy. What if I asked you for the hybridization? Well, what's the hybrid? First off, trick question, what's the hybridization on the hydrogen? There is none, right? It's just an S, unhybridized S orbital. What if I asked you for the hybridization on the fluorine? Well, fluorine has to send its electrons going up to that lone pair, to the right to that lone pair, down to that lone pair, and to the left to that bond. So that would be sp3 hybridized. Hope you're seeing kind of the pattern here. Okay, so on an exam, I could give you some big old molecule, and I could point to one specific atom, and I could say, what's the hybridization on that one atom? And that's how you'd figure it out, right? You'd simply look at how many different directions you need to send your electrons. Okay, now when it comes to those bonds, not all bonds are created equal. Okay, we know that some bonds are simply stronger than others, some are shorter than others. So for instance, if I'm looking at the hydrogen halides, so hydrogen bonded to fluorine, chlorine, bromine, and iodine, it turns out that hydrogen and fluorine, when they bond together, they actually make a really tight, strong bond. So it's a very, very short, strong bond. Hydrogen and iodine, on the other hand, make a much weaker, much longer bond. And if you think about it, it really makes sense. Hydrogen is a very tiny little atom, right? Fluorine is a very tiny little atom. Okay, so they can fit very closely together. Therefore, they can make a very tight, short bond. if I'm bonding that same small hydrogen with a big old massive iodine, it's much harder for that hydrogen to get in close to that iodine, right? There's just a lot of, kind of bulk there. And so therefore they make a much weaker, longer bond. It's like a long distance relationship, just not as strong as if you're in the same room together, right? Okay, you never should memorize these numbers or anything, but hopefully you can see that as we go from fluorine down to iodine, the bonds get longer, the bond strength gets weaker. Okay, what about the geometry of these? Well, hopefully you kind of remember this from Gen Chem, but we know that if carbon is sending its electrons in 4 different directions, we know it's sp3 hybridized, we say that that's a tetrahedral arrangement, bond angle of 109.5. Okay, if instead it's sp2 hybridized like this one, where it only has to send its electrons going 3 different directions, it's a trigonal planar molecule, and it has a bond angle of 120. It's called trigonal planar because it's a triangle, right? But it's also flat. It's in the plane. And then linear is easy, right? Because it's all just a straight line. So that's a linear sp hybridized bond angle of 180. Okay. Now, what about the bonds themselves? We've kind of already talked about this, but I would say that this is a sigma bond. This is a sigma and a pi. This is a sigma and 2 pi's. Okay. Now, just to try to circumvent any confusion that might arise later, turns out that sigma bonds are stronger than pi bonds. Okay, sigma bonds are stronger than pi bonds. Now, with that being said, people will often get confused because they'll say, wait, Mike, I thought that a triple bond is stronger than a single bond. And I'd say, you're right, a triple bond is stronger than a single bond. And you say, but you just said that sigma bonds are stronger than pi bonds. Well, it's because they're 2 different things, right? Think of it this way. A sigma bond is that initial overlap between these molecules. Okay, that's pretty simple, right? A direct overlap between things is going to be much stronger than this weak sideways overlap between them. So this direct overlap, this sigma bond, is much stronger than a weak sideways overlap of a pi bond. Okay, that's true. That's just the way it is, right? But when I'm talking about a single, double, or a triple bond, then I'm talking about the entire thing, right? If I said a triple bond is stronger than a single, yeah, it's because if I tried to karate chop all the way through that triple bond, that's going to be tougher than karate chopping through that single bond, right? Because here, all I'm doing is chopping through a sigma. Here, I'm chopping through a sigma and 2 pi bonds, right? So the sigma is strong enough already, and now adding 2 pi's on top of that, that's going to be a really tough bond to break through. So of course, a triple bond, the entire thing is going to be stronger than just a single, just a sigma bond. But this sigma portion is much stronger than a pi portion. Okay, you're going to see that as we do reactions. You're going to see that there are many, many times when we break a pi bond, but there are very few times when we break a sigma bond. And that's exactly why. Pi bonds are relatively weak, sigma bonds are relatively strong. So it's much easier to break a pi bond. Now there are very, very, very few times when we end up karate chopping and breaking through everything all at once. So that's very rare. You're not going to see that very often at all. So I hope that kind of clarified things a little bit. So here are some kind of practice ones for you to look at so that you can make sure that you can understand what kind of hybridization you might have. So let's just do one as an example. Let's look at that carbon right there. It's sending its electrons going to the left and to the right. Therefore, it must be sp hybridized. What about this carbon over here? Well, it's sending its electrons towards those 3 hydrogens, plus it's sending its electrons over to that carbon. It must be sp3 hybridized. What about this nitrogen? Well, better change colors. It's getting a little too messy here. Okay, let's say that looking at that one, it's sending its electrons off to that lone pair, as well as sending its electrons over to that carbon, two different directions, so it must be sp hybridized. Okay, I could also ask you how many sigma and pi bonds are in there, and you would say, well, it might actually be easier to draw it out fully just so that you can see everything. But this would be my molecule, right? Now, if I said how many of each type of bond do we have, I'll go ahead and go red for sigma. So 1, 2, 3, 4, 5, right? So I would say this contains 5 sigma bonds. Okay? What about pi bonds? Well, now I just need to look at what's left over. This second portion and the third portion of that triple bond would would comprise my 2 pi bonds. So I would say there are 5 sigma, 2 pi bonds in that molecule. I know this is a long chapter. You can always take breaks. You can come back as necessary, but we're almost done. Okay, so now we simply need to talk about bond strength and bond length. A single bond is going to be much longer and much weaker than a triple bond. Again, because a triple bond has a sigma and 2 pi bonds in it, right? So of course it's going to be shorter and stronger than a double, which is shorter and stronger than a single. Okay. It also turns out that the type of hybridization that we have is also important for determining the shorter and stronger our bond is. So looking down here, this carbon-carbon bond has 2 sp3 hybridized orbitals overlapping. That's going to be longer and weaker than this one that has an sp3 and an s. Okay, so yeah, turns out that basically the more s character you have, the shorter and stronger your bond is. It's easy to remember because you've got s, right? S for stronger, s for shorter. So something where I have an an sp overlapping with an s is going to be much shorter and stronger than an sp3 because it's basically the s character has been watered down, right? It's kind of like if you are a really big strawberry smoothie fan, and so for you, SP, oh, that's 50% strawberry and only 50% pineapple. Whereas over here, SP3 is only 25% strawberry and 75% pineapple. Of course, you're going to want this one. That's going to be your perfect choice, right? That's the shorter, stronger one for you. Okay. We've also talked about the bond angle, right? We already know those, so we're not going to worry about that. Okay. You do not need to memorize these charts, but it can be useful if you can't remember what's the bond angle for a specific hybridization, which one's shorter, which one's stronger. This chart might be useful for you. All right, so to kind of summarize that, remember that short bonds are also stronger. We also want lots of S character. That'll give us a short, strong bond. Those are the really important things that we've learned there. We know that pi bonds are weaker. Okay, so pi bonds are always weaker than sigma bonds. And then we also need to worry about what about the overall shape of the molecule. So for instance, in carbon dioxide, I know that oxygen is more electronegative than carbon because oxygen is up and to the right, right? So I know that it's going to pull electron density to the right. Now, what about the oxygen on the left? It's doing the same thing, but pulling electrons to the left. So what's happening overall? Well, they're canceling each other out, right? Those dipoles end up canceling themselves out, and so even though I would say that this has polar bonds, I would say that it is a non-polar molecule. Okay, so how do you know if something is a non-polar molecule? Well, there are two things that you should look at. First off, if I give you a molecule that consists of only carbons and hydrogens, like this one, you can automatically say with certainty that this is a non-polar molecule. Okay, so anytime you have just carbons and hydrogens, you are going to have a non-polar molecule. If you have a heteroatom, you suddenly see some oxygens or chlorines, it's going to be polar unless the dipoles cancel out. What I like to do is play one of these things is not like the other. So remember that game from Sesame Street? So if I had this molecule right here, I would look at this and say, well, I have a hydrogen and 3 chlorines around it. One of these things is not like the other. Therefore, that is a polar molecule. Now, what if this was a hydrogen? Well, I still have 2 hydrogens and 2 chlorines. They're not all the same. Therefore, polar molecule. What if I had 3 hydrogens around it? Still not. It's still a polar molecule, right? Because I have 3 hydrogens and 1 chlorine. One of these things is not like the other. Still a polar molecule. Okay. What if I did this and I put all chlorines around it? Now it's a nonpolar molecule, right? Because all 4 of them are the same. They all cancel each other out. So remember, if you see only carbons and hydrogens, it's nonpolar. If you see a heteroatom, then it's polar unless they cancel out, right? Which is pretty rare. Usually if you see a heteroatom, that's indicative that you have a polar molecule. Okay. You also have to take into account lone pairs when you're doing this. So for instance, if I have a water molecule, I have a hydrogen here, a lone pair here, a lone pair here. Are they all the same? No. Therefore, this is a polar molecule. Okay, same thing here. I've got a hydrogen, hydrogen, hydrogen lone pair. They're not all the same. Therefore, polar molecule. All right, that was it. I know that was a long one. It was a bit of a beast, but I hope it was a good review. Remember that if you need extra help on drawing Lewis structures, please check the description below.